Hello guys and welcome back. We are looking at, if I expand this is going to be 13F and we're going to do a few examples. This particular lesson is on finding the general solution to trig equations. Before we jump into what the general solution is and what this all means, we can actually do part of this example already just with our knowledge of solving for sine, cosine, and tan functions. So if I'm given a question like this, or I'm trying to solve for x, I want to solve for x, and the general solution is a general solution for x. So if I just solve for x right now with the knowledge I know, I could rewrite this as being 1 over 2, if I like. And this is going to be straight from my exact value triangles. If I come over here, I have 1/2. Cosine is adjacent over hypotenuse, which means 1 over 2 is going to have to be, x is going to have to equal pi on 3 or 60 degrees. Hopefully we're kind of getting used to seeing these enough that we could see that even without necessarily drawing the triangle. But if you want to draw the triangle, it's more than fine. This is where our values come from. However, because it's a cosine graph, I know that I have my unit circle. If I have a look at my all stations to central, if I have pi on 3, it means I have pi on 3, always taking my angle from the x-axis. It's going to be here, or it's going to be here. And again, that's because cos is positive in quadrant 4, and I have a positive value here for my fraction. So I have two possible solutions. I have pi on 3, or I have negative pi on 3. Now let's just consider, you might notice with this question, we don't have a domain, and this is kind of where it becomes more of a general solution type of question. In the general solution question, we're not given a domain. So what this refers to here is all about making a rule that's going to work for me solving any value of x based on my number of rotations. So if I know I go around the circle once or twice, I can simply just basically substitute that number of rotations into my formula and I can get my value for x. That's the idea of the general solution. So if I just focus here, just to help build this idea up, if I just focus on my solution here in the kind of positive or in quadrant 1, if I think about how I could get further solutions for x, I could go all the way around the circle. So let's actually start here. So I start at 0, I add pi on 3, I get to this line. Now I could continue going all the way around the circle back to here, and I could add another pi on 3, and I get a second solution. So if I add 2 pi, if I go all the way around the circle, one rotation is 2 pi. If I add 2 pi plus pi on 3, I'll get another solution, which looks like 7 pi on 3. So again, I'm just creating more solutions. And again, I want to start thinking about a general rule for what this looks like. And what I can say is I can say x is equal to my number of rotations around the circle. One rotation is 2 pi. If I'm talking about the number of rotations, it's going to be 2 pi multiplied by n, where n is going to be a whole number, and it's going to be my number of rotations. And I'm simply just going to add pi on 3. Now, if I think about this, if I kind of expand on this idea, well, if n is 0, I have 0 rotations around my circle. I just add pi on 3, and I get this solution here. If I go around my circle once, I go all the way around, that's going to be 2 pi plus pi on 3, I get my second solution, my third solution, I guess, in my list here. And if you can kind of keep thinking this through, this is going to work for every single solution for cos that's going to be in quadrant 1. However, we also have a solution in quadrant 4. And again, if I kind of think of it in with a similar idea here, then I'm going minus pi on 3. I go all the way around the circle again, minus pi on 3, all the way around the circle again, minus pi on 3. My pattern's pretty similar, except this time, instead of adding pi on 3, I'm subtracting pi on 3. So I could write this as being plus or minus pi on 3. That will give me every single possible solution to x when cos x is equal to 1/2. Now, in terms of how we could do this for other angles, this 2 pi n part's going to stay the same. And I'm just going to change this value based on what my solution is over here. So if this was root 3 over 2, then it would be pi on 6. But the idea kind of stays the same, where it's going to be my rotations around the circle plus or minus my angle for any cos function. So therefore, the general solution for cos x could be thought of as being x is equal to 2 pi n plus or minus, I'm just going to write theta, which is my angle based on my exact value. Now, I can actually, let's put this in a little box, and let's just simplify it for the sake of looking at some more simplified versions of these equations. Let's just put this, well, let's put this over there somewhere. Perfect. Let's just put my general solution to the side. I can actually continue simplifying this idea down. If I put both of these over the same denominator, that's going to become 6 pi n over 3 plus or minus pi over 3. Now, if we have a look, I've got a common factor of pi on 3. So that's going to become pi on 3 outside of 6n plus or minus 1. Now, this just makes it a little bit easier if I'm substituting in my rotations. So for example, again, if I go around 0 times, 6 times 0 is going to be 0. So I have pi on 3 times 1. I'm just going to be given pi on 3. So it still works. It's just slightly more simplified. It makes it a little bit easier to get to our answer. However, this is acceptable in the exam. So you can leave it something like that is fine. But I think it's always good to simplify as much as possible. So I've root 310, 3x is equal to 1. If I rearrange my left-hand side, I can divide both sides by root 3, and I get 1 over root 3. If I come back across to my triangle from before, tan is opposite over adjacent. My opposite side has to be 1. My adjacent side has to be root 3. So my angle must be pi on 6, which means 3x is equal to pi on 6. However, again, I have to consider my unit circle. So if I have a little look at my unit circle, I can see that tan is positive in quadrants 1 and quadrants 3, which means this angle here is going to be pi on 6, and also this angle here is going to be pi on 6. And again, just to reiterate, we always take our angle from our horizontal axis. So if I've got these two angles here, then I could say my second angle is going to be 7 pi on 6. Or a nice way to think of this is if this is pi, it's going to be pi plus pi on 6. Again, I'm going to go around 180 degrees. Then I'm going to add another pi. Now, this actually makes our solution a little bit more simple because I'm no longer talking about full rotations around the circle. I'm talking about pi rotations around the circle. What this means is that 3x is now going to be equal to pi times n plus pi on 6. Again, if n is 0, I just have pi on 6. If n is 1, I have pi plus pi on 6. So I've got solution 1, I've got solution 2. So it's actually a very simple solution for our tan functions because of this 180-degree relationship, or the fact that I essentially have a straight line here between my two angles as well. Also kind of works out well in my favor in that sense, because a straight line is 180 degrees or pi. So if I do this, that gives me this angle here. And I should have written this before as well, where n is an integer. So we're only going to have whole number values for n. Now, if I start kind of cleaning this up, because the difference here is I have a 3x, I want just to find the solution, or the general solution of x. So that means x is going to equal pi n on 3 plus pi on 18. I have pi on 3 as a common factor. Let's just do that. Pi on 3, it's going to be n plus 1/6. If I don't want to have a fraction there, I can take a 6, or I can kind of divide by 6 out the front. 3 times 6 is going to become 18, which is going to make this. If n is going to be 1/3 when I expand out, this must now become 6n plus 1, which again makes sense because I've taken 6 out the front. So I must have to multiply everything through by 6 on the inside. So I'm going to get this here, which again looks a little bit similar to my solution before, where I have this kind of 6n plus 1. In this case, it's just plus as opposed to plus or minus. There will be some subtle variations depending on the question. That just stems from whatever my angle is that I have over here on this side will give me a slightly different result. Okay, let's look at the third one where I have an angle that's either just x or some coefficient of x. The general solution for sines is a slightly more interesting one. Similarly to the first question, I'm going to divide both sides by 2 and get sine x is equal to root 2 over 2. Now, hopefully, some of us are realizing that this is kind of the simplified surd version of, this is the same as 1 over root 2, but I've just rationalized my denominator. So if I know this is 1 over root 2, that is going to be given when x is equal to pi on 4. So I've got my unit circle, and again, sign is positive in quadrant 1 and quadrant 2. So this time round, I have my angle here. If it's pi on 4, it's going to be pi on 4 on this side, and it's going to be pi on 4 on this side. And again, I'm going to work towards a general solution. So I have pi on 4, and I have 3 pi on 4. They're going to be my two solutions. Now, this time when I create a rule, it's a little bit harder to make this rule because I'm going to have 2 pi n. This time I don't have that 180-degree relationship. If I think about what I have here, if I just look at quadrant 1, I add pi on 4, I go all the way around, I add another pi on 4. So it's more similar to cos in the sense I'm dealing with full rotations. So we're going to have 2 pi n plus pi on 4. That part's really similar to the first example we did. However, I can't simply just do a plus or minus, because if I subtract, then I'm in quadrant 4. I have signs negative in quadrant 4. This whole thing doesn't really work in that way. So instead, what I need to do is think about, well, if I do 1 full rotation, how do I get to 3 pi on 4? And the answer simply is I just add 3 pi on 4. So it's slightly less neat, it's slightly less clean. So we're going to do a few little things to make this a little bit neater. So again, if n is 1, I have 2 pi plus pi n, sorry, plus pi on 4. I also have 2 pi plus 3 pi on 4. I'm going to keep getting my solutions. Just bear in mind, if n is equal to 1, I can put that in either one to get my same answer if I do 1 full rotation. To make this a little bit neater, though, let's take out our common factors. This is going to become, let's take out pi on 4. This is going to become 2 pi n. Oh, if I put this over 4, that's going to become 8 pi n over 4 plus pi on 4. Then this is going to become 8 pi n over 4 plus 3 pi on 4. So if I take pi on 4 out the front, that's going to give 8n plus 1. Same idea here. That's going to become 8n plus 3. So I've got my two solutions here. Yep, 8, that makes sense. And you notice that this part here is similar, but not quite the same. My common factor is exactly the same. So there is a way to kind of simplify this or to form one equation. To do that, I'm going to do something that's a little bit similar to what I did when we looked at the mathematical induction questions, where I can introduce kind of a plus minus situation. So I'm just going to show you guys this. Pi on 4 is common to both. 8n's common to both. And now I'm going to write plus 2. Let's do this in red. Plus or minus 1. So if I add 1, I get 3. If I take 1 away, I get 1. So 2 plus or minus 1 is 1 or 3. That gives me each of my solutions here, depending on if I'm plussing or if I'm minusing. So in order to solve for my general solution for something like this, and I've chosen example B because I think that's going to be the most interesting, is it's going to be similar to before. I look at my exact value triangles and I get now, instead of just x or 3x, I'm going to get 2x minus pi on 3 is going to be equal to pi on 4, because tan of pi on 4 is equal to 1. If I draw my unit circle, I'm going to have pi on 4, and I'm going to have pi on 4 over here. So again, similar, very, very similar to part B from the question we did before. Now that I've got this kind of relationship here going on, I've actually done a question like this. So I know I'm going to get something that looks like, for my general solution, it's going to look like this: pi n plus pi on 4. And again, if n's 0, I have my first one. If n's 1, I keep going around my circle to get all of my solutions. However, this time around, I don't have 3x. I have 2x minus pi on 3. So I'm going to add pi on 3 to both sides. That's going to give 2x equals pi n plus pi on 4 plus pi on 3. And essentially, the difference here is I just need to do a bit of an algebra manipulation or an algebra kind of rearrange to get a more simplified answer. So if I add a quarter plus a third, I can make them both a denominator of 12. That's going to give 7 pi on 12. That's equal to 2x. Now I can divide both sides by 2. I'm going to have x equals pi n over, actually, pi on 12. I'll give myself a little bit of space because I have a lot of common factors in here of pi. So that is going to equal pi on 2 outside of n plus 7 over 12. 7 over 12 is a little messy. Let's bring 12 out, and that's going to give pi over 2 times 12 is 24. That's going to be 12n plus 7. So that's going to be my general solution for something like this. Again, the original premise is the same. I just have a more complex algebraic simplification at the end. And I actually think as a general rule, especially if it's, you always want a solution in terms of x. So like I said, for the first time we did this. So for the first time, I did say this is acceptable. I do think it's actually is good practice to always get it as simplified as possible. Have a think about how I'm going to mark a question like this in the exam and if that's required. Either way, I think let's actually make that a rule now. If you do get a question like this in the exam, simplify your algebra as much as you possibly can. You will see the textbook does state the general solutions like so, which is also good to know. This is the kind of the same thing we've done just before. Hopefully this makes a little bit of sense with the general solution stuff. If you guys have any questions, feel free to ask me in class.